All right, so today we're going deep into AI art, and more specifically, those amazing images you've been seeing everywhere. The ones made by diffusion models, you know the ones I mean.
Right.
Like, have you ever thought, are artists going to be replaced by robots?
Hmm.
Well, that's exactly what we're going to unpack today. Like, how do these things actually work? And is AI art really art?
Yeah, there's definitely a lot of buzz around AI art these days, and a good amount of concern, too.
For sure. And that's what makes this all so interesting. We've got these models making these incredible images, super high quality, totally unique. But there's this worry that they're really just copying, like just memorizing data.
Yeah.
So how can both things be true? That's what we're going to figure out today. And we got some really cool research to help us do it. It's from NYU and the Flatiron Institute. And they've done a deep dive into how these models work. And some of their findings are pretty mind-blowing.
Yeah, mind-blowing is a good way to put it. The math behind this stuff can get pretty hairy, but I think we can explain it in a way that makes sense.
Well, that's why you're here. I'm good with the big picture stuff.
Yeah.
But you're the one who can break down all the technical stuff. So let's start with the basics. How did these diffusion models actually make images? It seems like magic. Like pulling pictures out of thin air.
Okay, so imagine you've got a photo, a really clear one, and you start adding noise to it, little by little, until it's just a mess of pixels, Totally random. A diffusion model basically works by reversing that process. It starts with pure noise, and then it figures out how to remove that noise, step by step, until boom, there's a recognizable picture.
Oh, wow. So it's kind of like having a blurry puzzle, and then you slowly put it together until you can see the whole image.
Exactly. The model learns to do this by training something called a denoiser. It's basically an algorithm that's really good at removing noise from images.
Okay, so it's like super-powered Photoshop expert.
Hmm.
But how does it know what noise to remove? That part still seems kind of magical.
Right. Well, this is where it gets really cool. The denoiser actually learns from looking at tons of images. It figures out the patterns, the relationships between different pixels. It's basically learning the visual grammar of images.
So it's not just randomly deleting pixels. It's learning the rules of how images are made.
Exactly. And the more images it sees, the better it gets at understanding those rules. And that means it can not only remove noise, but also create entirely new images, images that follow those same rules, which is how we get those amazingly realistic AI-generated pictures.
Wow, that's incredible. But okay, let's talk about the elephant in the room. This worry that diffusion models are just copying, that they're memorizing images they've seen before, instead of making something truly new. How does this research address that?
Yeah, that's a big question. So to figure that out, the researchers did a really clever experiment. They trained separate denoisers on two different types of images, faces and bedrooms, and they kept making the data sets bigger and bigger.
So they were testing if the models were just getting really good
Yeah,
at copying specific faces or bedrooms they'd already seen.
right. And at first, when the data sets were small, that's exactly what seemed to be happening. The models would spit out almost exact copies, or kind of jumbled up versions of images from the training data.
So it seemed like the whole AI as a copycat argument might be true.
It did. But then, when they made the data sets much bigger, something amazing happened. The models trained on different sets of faces started creating almost identical images, even though they'd never seen the same pictures.
Wait. So they were shown totally different faces, but ended up making similar images. That's both creepy and awesome. How is that even possible?
Right, and that's where this idea of model variance comes in. When the variance is high, it means the model is overfitting, basically just memorizing.
Yeah.
But when the variance is low, like it was in this experiment, it means the model is actually generalizing. It's not just copying specific pictures. It's learning something fundamental about faces in general, like their structure, the way light and shadow work, the things that make a face a face.
Well, it's not a photocopier. It's more like an image composer.
Yeah, that's a great way to put it. They go beyond just mimicking to understanding.
So how are they doing that? The paper talks about something called geometry adaptive harmonic bases, or GAHBs for short. And I have to say, that sounds a little intimidating.
Yeah, it's a mouthful, but it's not as complicated as it sounds. Remember how we were talking about the denoiser and how it shrinks the noise along certain directions in the data? Well, those directions are called a basis. It's kind of like a coordinate system that helps the model navigate through all that noise to find the image hidden underneath.
Okay, so the denoiser has like a special map that guides it through all the random pixels.
Exactly. And what the researchers found is that these diffusion models, especially the ones using deep neural networks. They have a strong preference for using a specific type of basis, GAHBs. And these GAHBs are really sensitive to the shapes and patterns in an image.
Interesting. So they're not just removing noise randomly. They're targeting the noise that's hiding the important parts of the image, the stuff that makes it look like a face or a bedroom.
You got it. And if you were to actually see a GAHB, it would look like a bunch of wavy lines that kind of trace the outlines and textures of an image. We've got a picture in the show notes. You can check it out. And you'll see how those wavy lines are like a map of the image's DNA.
Wow, that's really cool. But why are these GAHBs so important? What do they tell us about how these models work?
Well, this bias towards GAHBs seems to be the main reason why diffusion models are so good at generalizing. It's like they're not just learning specific noses or eyes, they're learning the building blocks of any nose or eye.
So they're learning the principles behind those features, not just the features themselves.
That's it. And that's huge because it changes how we understand these models, their strength, their weaknesses, and how we can maybe make them even better.
This is already making me think about AI art in a whole new way. It's not just about copying, it's about finding patterns and connections that we might not even notice as humans.
Right. It makes you wonder about what creativity really is.
Yeah, it really does.
So, to test this whole GAHB idea, the researchers got even more creative with their experiments. They went beyond photos and started testing how the models worked on different types of images.
Okay, I'm intrigued. What kind of images?
So first, they used something called Chi images, which are kind of like artificial images where you can control how smooth or detailed they are. They're like test patterns for the AI.
So they wanted to see how the models did in a more controlled environment.
Right. And the results were pretty interesting. The DNNs did really well with these Chi images, like almost perfectly matching what the theory predicted. If they were using a GAHB-like basis, it was like they were made for this kind of image.
Okay, so one point of the GAHB theory, what was the second type of image they used?
For the second test, they used images of what are called low-dimensional manifolds. It sounds complicated, but just imagine a simple shape, like a disk, moving around in a picture, so the only things changing are its position and maybe its size. That's what makes it a low-dimensional manifold.
Oh, I see. It's like taking pictures of a bouncing ball.
Exactly, and on these manifold images, the DNN still did well, but there was a twist. Their reliance on GAHBs actually made them a little less efficient in this case, because GAHBs are really good at capturing complex shapes and contours. But these shapes were simple and smooth, so a different kind of basis would have been better.
So they were using the wrong tool for the job.
Kind of, but the important thing is, even though they weren't perfectly optimized, the fact that they still relied on GAHBs shows that this bias is really deep in these models. It's like their default setting.
Fascinating. Okay, so that's two types of images. What was the third one?
Okay, so for this one, they took the same faces they'd used before, but this time, they shuffled all the pixels around randomly.
Just old faces. So like taking a portrait and scrambling it up.
Exactly. And unsurprisingly, the DNNs really struggled with these scrambled images.
That makes sense. All those spatial relationships, all the patterns that GHHBs were so good at finding were totally gone.
Exactly. And this just shows how important GAHBs are for these models. They're awesome at capturing those spatial relationships, but when you mess those up, they don't work as well.
Okay, so we've talked about the basics of how diffusion models work,
Mhm.
the memorization question,
Yeah.
and this whole GHB thing. That's a lot of ground to cover. But what does it all mean?
Well, I think the biggest takeaway is this. The reason DNNs are so good at making images is probably because of their ability to find and use GAHBs.
So they're not just randomly putting pixels together, they're tapping into these fundamental patterns.
Exactly.
And that helps us understand their strengths and limitations.
Yeah. It's like a window into how they learn, why they struggle sometimes, and how we can make them even better.
This is making me rethink how I see AI art.
Right.
It's not just about imitating, it's about uncovering hidden connections.
And it raises all sorts of questions about what it means to be creative.
It really does. I think it's a good place to pause for now. We've covered a lot in this first part of our deep dive into diffusion models.
Yeah, we have. It's a lot to process, but it's important groundwork for understanding the future of AI and creativity. So welcome back. I'm excited to dig more into those implications you mentioned, about diffusion models and GAHBs. What does it all mean? Like practically speaking.
Yeah, me too. This GAHB thing has been a real eye-opener.
Yeah.
But I'm wondering what it means for the future of AI art. Does it give us more control? Or does it make the art less impressive somehow?
Those are great questions. And I think that's why this research is so important. For one thing, Knowing that diffusion models are so good at finding these patterns, these GAHBs, it explains why they're so good at making realistic images. They've tapped into something fundamental about how our visual world works.
So it's not just about throwing more computing power at it, it's about understanding the data itself,
Yeah.
like uncovering the hidden rules of how images are made.
Exactly, and that opens up a lot of possibilities. For example, knowing about GAHBs could help us design new models or new ways of training them that take advantage of this bias. Imagine being able to control how realistic an image is just by tweaking how the model uses GAHBs.
That's wild. So we could make even more realistic AI art, or even surreal art, by working with the model's natural tendencies.
Exactly. It's all about understanding the tools we're using, what they're good at, and what they're not so good at. This research gives us a much better understanding of that.
This is making me see AI art in a whole new light. It's not just about mimicking, it's about finding connections
Yeah.
that we might not even be aware of.
Yeah. It makes you think about what creativity really is
Yeah, that's
and where these models fit into that.
for sure.
So, to really put this GAHB theory to the test, the researchers took things a step further. They went beyond just photos and started using different kinds of images.
Okay, I'm listening. What kinds of images?
Well, first, they use these things called key images. They're basically artificial images, where you can adjust how much detail they have, like test patterns for AI.
So they wanted to see how the models performed in a more controlled setting.
Exactly. And the results were pretty amazing. The DNNs were almost perfect with these key images, like they were practically made for them.
Okay, so that's one for the GAHB theory. What was the second type of image?
Okay, so for the second test, they used what are called low-dimensional manifolds. It's a bit of a technical term, but just picture a simple shape, like a circle, moving around in an image. The only things that change are its position and size. That's what makes it a low-dimensional manifold.
Oh, I get it. Like taking pictures of a ball bouncing.
Exactly. And with these manifold images, the DNN still performed well, but their reliance on GAHBs actually made them a little less efficient because GAHBs are so good at capturing complex shapes. And these were simple shapes.
So they were using a sledgehammer to crack a nut.
Yeah, something like that. But the point is, even though it wasn't the ideal situation, the fact that they still use GAHBs shows how deeply ingrained this bias is.
That's interesting. It's like they can't help but see the world through this GAHB lens.
Yeah, exactly.
So we've got two types of images down. What was the third one?
All right, so for the third test, they did something pretty wild. They took the same faces they used before, but they shuffled all the pixels
So
around.
shuffled faces. So like a completely scrambled portrait.
Exactly. And as you might guess, the DNNs had a really hard time with these shuffled images.
Oh, yeah. All the spatial relationships were gone.
Yeah,
All the patterns the GAHBs were so good at picking up.
right. And this just highlights how important those spatial relationships are for these models to work.
It's like they need those visual cues.
They do.
So, okay, we've talked about how diffusion models work. We've talked about memorization, and we've explored this whole world of GAHBs. But
Yeah.
what's the big takeaway for our listeners?
I think the most important thing is this. This research shows us that the success of these models might be mostly because of this hidden talent for finding and using GAHBs.
So they're not just throwing pixels at a canvas, they're tapping into these underlying patterns.
Exactly. And that helps us understand how they work and why they're so good at what they do.
And maybe even how to make them better.
Right.
This is really making me rethink how I see AI art. It's not just about imitation, it's about finding connections that we might not even be aware of.
That's a great way to put it.
It's like AI is giving us a new way to see the world.
I like that.
And it makes you wonder if they can find these hidden patterns in images. Could they do the same thing with other types of data?
That's a fascinating question, and it's something researchers are definitely exploring. Imagine using these models to discover new musical melodies, or hidden meanings in ancient texts, or even patterns in astronomical data that could point to new planets.
Okay, now you're just blowing my mind.
But it's not that far-fetched. If they can do it with images, why not other kinds of data?
It's like AI could be a partner in scientific discovery.
Exactly, helping us unlock secrets of the universe.
I love that idea. AI is a partner, not a replacement.
Exactly. It's about collaboration, bringing together the best of both worlds.
Okay, so we've talked a lot about what this means for AI. But what about for us, the people using this technology? How should knowing about GAHBs change how we see AI-generated images?
That's a great question. Does it mean the images are less creative? Less original?
Yeah, that's what I'm wondering. If they're basically following a set of rules, even if those rules are really complex, does that make their art less impressive?
I think it's important to remember that human artists also follow rules, whether they realize it or not. Every artistic style has its own set of principles.
So you're saying even human creativity has constraints.
Of course, we're all shaped by our experiences, our culture, our influences.
But what about the fact that these models learn from huge data sets of existing images? Does that mean they're just remixing old stuff?
It's true, they're influenced by the data, just like human artists are inspired by the work of others.
So it's not copying. It's more like building on what came before.
Exactly. And the way they combine those influences can lead to really unique results.
It's like they're taking the raw materials of creativity
Yeah.
and forging them into something new.
That's a great way to put it.
And that's what makes this whole field so exciting.
It really is. It blurs the lines between human and machine creativity and makes us rethink what art even is.
This has been a really thought-provoking conversation. It's clear that diffusion models are more than just algorithms. They're powerful tools for understanding and expression.
And we're just starting to explore their potential.
I can't wait to see what happens next.
Me neither.
Okay, so we've really gone deep on these diffusion models, haven't we?
We have.
We've seen how they work, this whole GAHB thing, and even what it means for creativity.
It's been a wild ride.
But before we wrap things up, I want to leave our listeners with something to think about, something to chew on.
Okay, I'm intrigued.
So we've talked about how these models are amazing at finding patterns.
Yeah.
But what if, instead of asking them to follow those patterns, we ask them to break them?
Oh, wow.
Like, what if we challenge them to create images that are totally unexpected, that defy what we think an image should look like?
That's a really cool idea, like asking an AI to be an avant-garde artist.
Exactly. Could we use these models to create a whole new kind of art, something that goes beyond realism and explores totally new visual territory?
It's possible. Imagine images that are beautiful, but also kind of unsettling, images that make us question what's real.
Yes. Images that challenge our ideas about art and spark new conversations.
It's like looking through a kaleidoscope, where the shapes and colors are always changing.
That's a great analogy.
And it speaks to the potential of this technology to not just imitate,
Yep.
but to innovate.
And to inspire.
Absolutely.
I think it's important to remember that even with AI, the real creativity comes from us.
Right.
It's our ability to ask questions, to explore new possibilities. That drives innovation.
Exactly.
So as we move into this future of AI-generated art, let's remember to be open to the unexpected, to challenge our assumptions, and to keep asking, what if?
I love that. What if? That's the heart of it all.
This has been an amazing conversation. Thanks for walking us through all this.
My pleasure.
And to our listeners, thank you for joining us on this deep dive.
Yep.
We hope you've learned something new and that you'll keep exploring this amazing world of AI art.
And keep asking questions.
Until next time, keep learning, keep creating, and we'll see you on our next deep dive.